So recall from last class that on a complex, so V is a finite dimensional complex vector space, and a Hermitian form on V is a map on V cross V to C that is conjugate linear on the first factor linear in the second factor and Hermitian symmetric, which is that if you swap the order, you get the complex conjugate. This is for all V, W, Vi, Wj inside V, and for all alpha I, beta j inside C. Okay, so this is
Sir,
what.
Could you just scroll up a bit?
Yeah.
Okay, sir.
Yeah, so conjugate linear on the first factor, linear in the second factor, and I mean again that is a convention, but we will just follow whatever convention Artin's book has chosen, just so that it's not too confusing. First time I see it's yeah. This is, okay. And we also talked about the standard Hermitian form. On Cn is this vector alpha 1 through alpha n, beta 1 through beta n. This is alpha I bar beta sum over that. Okay. And so it is just, so we can write it as, if I call this thing x and this thing y vectors, then this is just conjugate transpose y. Okay. This is the definition. This is conjugate transpose and then conjugate individual elements. Okay. And note that if you apply the standard Hermitian form to a vector, we would just get the square of its length. If you express this in real coordinates, it would be real of alpha I squared plus real imaginary part of alpha I squared and so on. So it is the usual length of that vector. So this is what we did last time. Okay, so we want to develop this further. Definition. Complex matrix. Okay. So of course, I am not saying that it is not a real matrix. It is just that the entries are complex numbers. Doesn't necessarily complex conjugate.
Sir, if you're speaking, I don't think we can hear you.
Okay, but you can see my screen, can you not?
Yes, sir. Yes, sir.
Just saying, sorry, from my office, I keep.
Sir, also your voice is breaking a lot.
Okay, am I audible now?
Yes, sir.
Okay, sorry, this, yeah. So this is the complex, the adjoint of A is this one. In other words, the ijth entry of the joint is the complex conjugate of the jith entry of the given matrix. I mean, okay, so this is, sorry, I should say, this is this is so analogous to formulas where, so if you take the sum of two matrices, their transpose is the sum of their transposes, etc. Okay, so we have the following. If you take a scalar times a matrix and then ask for its adjoint, then it would be just then if you have AB and this, so this is for all matrices A and for all little c in complex number matrix. Okay. So this is all matrices A, B, and definition. We say that a matrix is Hermitian or sometimes called self-adjoint. Or self-adjoint. Okay. If A star is A. Okay. So this is the notion analogous to real symmetric matrices. So it is, I mean, right now we're just making some definitions for complex matrices, which is just sort of parallel the corresponding definitions for real matrices. Okay. The only thing, okay, so just give me a minute. It's okay. We'll come to it. Yeah. Okay. So this is self-adjoint. Okay. So observation. If A is a Hermitian matrix, then the diagonal entries are real. Why is that so? Since I bar must be equal to, I mean, this is the ith entry of the I, ith entry of A star. I bar is by definition the ith entry of A star. Okay, but by because it is Hermitian, that is A star is equal to A. And this is just AI. Okay, this is the reason. Okay, so this is an observation. This is only a necessary condition. Okay? So, for example, if we have one, let us say 2I and minus I. Sorry, I'm just winging it. So I'll have to check. A star is so you have to transpose this. So you get a minus I here and I here, and then you conjugate the whole thing. So this is 1 I minus I. Sorry. So this is so you have to transpose it and then apply conjugates for everything, and that we get the same answer. Okay, so this is a Hermitian matrix.
Sir,
Yeah.
could you scroll up for a minute?
Yeah. Here or the still
Yeah,
further
no,
up?
okay, yeah.
Yeah. Okay. So definition. Let be a Hermitian form. Okay, on V, and V1 through Vn be a basis of V. Okay. So then, okay. So let A be the matrix with Vi, Vj as the ijth entry. So, okay, so this is called the matrix of thing. A is called the matrix of this given form with respect to the basis, the given basis. Okay, so we're going to prove something similar to what we did for real forms, symmetric forms. Okay, proposition. Okay. So I mean, okay. So yeah. So we haven't actually. Sorry, just a minute. What did we say? If yeah. So we talked about Hermitian matrices. Okay. So from the definition, it would. Okay, so it would this matrix here is a Hermitian matrix. I'll write down just, but that's where I'm heading. Just to give you a heads up. Okay, so this is a Hermitian form. So if you switch the roles of Vi and Vj, then we would get Vj. I mean Vj comma Vi bracket Vj comma Vi will be bracket Vi comma Vj bar. Okay, so the ijth entry of the jith entry of A is the ijth entry bar, conjugate of it. Okay, so that's where we that's what I'm going to state now. Okay. Let A be the matrix of a Hermitian form okay, on a complex vector space V. Okay, with respect to a basis B. Okay. Then A is a Hermitian matrix. So that's the first observation. Okay. But why? I mean, why are we concerned about this matrix? So this is similar to the thing that we saw okay, for real symmetric forms. So let V and W be inside V, and X and Y be inside Cn. So let us say that n is the dimension. So just sorry, I should have added that here. N is the dimension of V. Okay, so this B has n elements. X and Y inside Cn okay, be the vectors corresponding to V and W in the basis B. Okay, so that is well defined. I mean, okay, given any basis, one can then. So this is the next. So maybe I should just label these things. 1, 2. This is X transpose A, X conjugate transpose A, Y. So this is why. So starting from a Hermitian form, how do we express it as a vector matrix vector multiplication? This is what it says. Conversely, if A is a Hermitian matrix, okay, then the form X transpose AY defined on Cn. N is sorry, Jesus. N is an n by n Hermitian matrix, then the form on this is the form on Cn. This X and Y Hermitian. Okay. Parse the statement, and then we would proof is not at all difficult. It is entirely analogous to the proof for the real symmetric case, but I will still sketch it so that we are okay with the proof. Okay, but let us parse the statement before we try to prove it. So now, in the first half, we are given a Hermitian form on some n-dimensional complex vector space V. And as earlier, we have defined the matrix A with respect to this given basis V. First claim, A is a Hermitian matrix. Second claim, this product, I mean, this bracket V comma W is given by X star AY, where X and Y respectively represent V and W with respect to the spaces. Okay. So that's the first half of the proposition. Second half is a converse statement. That is, if we start with the Hermitian matrix and we define bilinear form on Cn using this formula, then it would be a Hermitian form. Okay. So again, just to emphasize, or maybe just to reiterate, Hermitian for complex, in the complex setting is is entirely parallel to the theory of real symmetric setting. Okay. Just to what is this thing? Conversely, phase the form on Cn. What is this? Okay. So I hope the statement of the proposition is clear. Okay. Once you write out the proof, it will become. You'll see that it is actually the similar proof as the real symmetric case. But I will still nonetheless sketch this just so that you don't miss it. Okay. So now we are assuming that this is a Hermitian form. Okay. Then A J I, this is Vj Vi. This is because it's a Hermitian form, this is Vi Vj bar. This is Ai J bar. Okay, for all I and j. So this proves one. One was only this assertion. I just wrote it so that it is stated. It is not all that it is using is so this uses that form as Hermitian. Okay, so that's a proof of the first statement. Okay. The second statement is that concretely this form can be described by this multiplication. So that is the same, similar proof. Okay. So VW, So write the elements. So write B as V1 through Vn. We didn't label the elements of B yet. Okay, so just so as this. Okay, so then VW is so we also need to write X as X. Okay, X as alpha 1 through alpha n, and Y as beta 1 through beta n. Okay, so then VW is just sum over I, alpha I V I W. This is alpha I bar, sum over I, alpha I bar V I W. Let me now write that as beta J W J. Okay. This is now alpha I bar, sum over I, then sum over J, V I W J, beta J. I just wrote the beta J on this side to emphasize this point, which is just X star A. So this proves true. So now conversely, actually I leave the converse as an exercise. Okay. I think if you understand how this is being argued, then I think the converse should not be difficult. I mean, actually, converse does not. It is sort of an explicit calculation. Just check whether it is conjugate linear on the first factor, linear on the second factor, and it's Hermitian symmetric. Okay. So now, yeah. So actually, just one suggestion. See, there are sort of I mean, I mean, the whole thing could be a little confusing. I would, even after all this, even when I teach, I'm still confused as to whether if I say this, I mean, if I make some statement, whether it will be confusing to students or not. So it is this. So I would suggest that along with my notes, you read Artin also. There are sometimes he makes some pertinent remarks which may clarify things. Okay, so for example, in the previous section at the end, he makes a remark about not getting confused between P inverse AP, which is used for when we study linear transformations and change of basis, as opposed to P transpose AP, which is what preserves the bilinear form, although it's the same matrix. Okay, so these things can be a little confusing. So it is probably better that, and Artin makes it a point to make these remarks. Okay, so I would urge you to just sort of read along and also think about these things, because as I said, there are stuff. I mean, this is probably a little bit more confusing than or less straightforward. Sorry, I should not say straightforward. This sort of calculations are very simple. Okay, but it is probably okay. Let us use confusing itself to than just studying linear transformations. Okay? So these are not, we are not studying linear transformations now. Okay? So that is just one thing to keep. Although we are doing the similar calculations with matrices. Okay? So just to keep that. Okay? So please do read along and think about things. Okay. So definition. Hermitian form is positive definite. Okay, if this thing is greater than 0 for all V inside, all non-zero. I mean, on a vector space V non-zero. Okay, just so that it makes sense. Okay, recall that since it is a Hermitian form, okay, this is same thing as it's. So if I swap the V and V, I should get the complex conjugate transpose, complex, not transpose, just conjugate. Okay, so this is so this V is inside R for all V inside. For arbitrary vectors, the bracket thing V bracket W need not be inside the reals. Okay? But for the same vector, V comma V is always a real number. Okay. So this is so. So we say that it is positive definite if this real number is positive. And a Hermitian matrix A, meaning self-adjoint matrix A, is positive definite if X transpose AX is positive for all non-zero X inside Cn. Okay, vector in Cn. Okay. Okay. So now, so this is just some definition, and it follows from the previous proposition that a form is positive definite if and only if the corresponding matrix is positive definite. Okay. So maybe I'll just remark that thing, but leave the proof as an exercise. Okay. Yeah, and okay. So again, change of basis. So suppose that B prime is another basis of V, okay, and P is the invertible matrix such that for all V inside V, okay, the coordinate vector of V in B, okay, is P times the coordinate vector of V in B prime. Okay, so I hope the statement is clear. I mean, at least the okay. So B and B prime are bases of V, and okay. So given any given any vector V, they can be represented by coordinate vectors. I mean, vectors in Rn, vectors in Cn corresponding to with respect to these two bases. So coordinate vector with respect to B is P times the coordinate vector with respect to B prime. Suppose P is P is this matrix. Okay, the change of basis matrix, okay, with this property. Okay, then the matrix A of the matrix in the basis P prime is P conjugate transpose A P. Okay. Proof. Okay. So the point is that we would evaluate V comma W in two different ways. Let VW be inside V, okay, and with coordinate vectors. Okay, so let us let x and x prime be the coordinate vectors of V with respect to B and B prime respectively. Okay. Similarly, let y and y prime be the coordinate vectors of the same sentence, just for you. Okay. So then what do we have? VW can be evaluated in two different ways. On the one hand, it is X transpose A prime X transpose hold on, which way I want to write it in terms of B prime, like A. Okay, so maybe I write like this. Okay. On the one hand, it is X prime transpose A prime Y prime. Okay. So this is it being calculated using B prime. Okay. On the other hand, okay, it is X transpose A Y. Okay. Now the vertical thing was calculated using B prime. The horizontal thing is calculated using B. But I want to now use the change of basis matrix for this one. X is P times X prime. Y is P times Y prime. So P X prime transpose A P Y. This is X transpose star P star A P Y. So we have this equality. Okay. So and this is true for every X prime and Y prime. This is a Y prime here. This is true.
Sir, shouldn't it be Py prime?
Yeah, I've changed. I said Y, but here you mean. Yes, correct. Py prime. This is true for every X prime and Y prime in Cn. Okay, so A prime is P star A P. Same argument. You can pick out the ijth entry of a matrix by sending on the left side. You use the ith standard basis vector, and on the right side use the jth standard basis vector. That will pick out the ijth entry. So if you do, since this is true for everyone, it will say that the ijth entry for these two matrices are the same for every I and j. Therefore, the matrices are the same. Same argument from last time. So as I said, in many ways, the theory of Hermitian forms on complex vector spaces is analogous to the theory of symmetric forms on real vector spaces. Okay. Okay. So now comes an extremely important property of Hermitian forms. The eigenvalues of a Hermitian matrix are real. Okay. Not only the diagonal entries are real, in fact, the eigenvalues themselves are real. Diagonal entries are real because it is self-adjoint. Okay, so this is an extremely important property, and Okay, I don't know. Okay. So so let X inside Cn, let A be a Hermitian matrix. And X inside Cn be an n by n symmetric matrix, and X inside Cn be an eigenvalue, eigenvector with eigenvalue lambda. Okay, so then X transpose A X. This is just X transpose lambda X eigenvalue. This is just lambda times the usual usual standard Hermitian product. Okay, sorry. Okay, I should clarify. Maybe I should not have used that phrase. It is just for X that you get X star X. We are not saying that A is. Maybe I gave the wrong impression. I am not saying that A is the standard Hermitian product, or A can be represented by the standard Hermitian product. It is just that when you apply it to X, the pair X comma X, it would be just lambda times X star X. So this is the first thing. So now, okay, so this is, maybe I should clarify. This is associating it like this. Okay. So now we can associate it in another way. Okay, as X star A times X. Okay. So this is X star A is just A star X star. Okay. No, yeah, correct. Okay, times X. So inside the brackets, I'm just rewriting it like this. But A is Hermitian, so this is just AX star X. Okay. This is where the Hermitian A is Hermitian is used. Okay. Now, but A is X is just lambda X star X, and this is lambda bar X star X. Yeah. Okay. Sorry, not lambda prime, lambda bar, lambda bar. Okay. So these are okay, and so this one says that lambda equals this. Lambda is inside. Okay. So this is an important property of Hermitian matrices, and from this we see a corollary that the eigenvalues of a real symmetric matrix are real. Okay. And the proof of the corollary is that if A is a real symmetric matrix, okay, then it is Hermitian. When thought of as a complex matrix. So this is the yes, this is an important property of I mean both for complex Hermitian matrices and as a consequence for real symmetric matrices. Okay.
Sir, so we can
Yeah.
just say that if an eigenvalue exists, then it is real, right?
No, eigenvalues always exist as complex numbers.
Oh, okay.
Yeah,
Yes, yes.
those, I mean,
Yes.
yes. Sorry, maybe I should. Yeah. Sorry. What I meant is, I mean, that sounds a little awkward, but the complex eigenvalues of a real symmetric matrices are real. That's what is being said. Is that clear now? But let me not write
Yes,
that.
sir. Yes, sir.
Very awkward sentence. So let me not write it. Okay. Yeah. Okay. Okay. So just okay, so I'll just make one definition, but these things will make. It's okay. Let me skip the definition. Okay. Okay. So this is about Hermitian matrices. Okay. So now we want to discuss. So I'm sorry. I'm more or less following the book linearly. Okay. Some things I will postpone for later when it may start making sense, like unitary matrices, etc. But otherwise, I am sort of following the book linearly. So this is now I'm going to start orthogonality. Okay. So the idea is to have a notion. I mean, to develop a notion. So this will. So especially this section, I think you should read because and think about it, because there is some discussion. There's a parallel discussion for real matrices and complex real symmetric forms and complex Hermitian forms. They are they are parallel and they're syntactically the same statements, but they mean different things for complex matrices and for real matrices. So it is better that you read this section along and sort of internalize the distinction between the two, as well as the discussion is the same, that part. Okay, so a notion of analogous to the usual dot product that we have. Okay, so that's the aim of this section. Okay. So this denotes either, I mean, okay, so maybe I should start saying V denotes either a real vector space or a complex vector space. Okay, so you might ask, well, every complex vector space is also a real vector space, so why make the distinction? Well, it becomes clear. We want to look at these bilinear forms, and in that case, we want to make a distinction between a real symmetric form and a complex Hermitian form. Okay? So, though the discussion is the same, I mean, syntactically the same, one should keep the distinction in mind. Okay? So, this denotes a real symmetric form if V is a real vector space or a complex Hermitian form if V is a complex vector space. Okay. So now we will. So remember that we started out by thinking about this bracket thing, V bracket W, as a way to generalize the notion of a dot product. Okay. Define a notion of perpendicularity. Say that maybe this is definition. Say that V is perpendicular, orthogonal. Perpendicular is probably should be restricted to the word when we discuss usual dot products. Orthogonal, okay, if V, V is orthogonal to W, or if VW is 0. Okay. So we denote this, we use VW to denote this. Okay. So we have a bilinear form, symmetric, a symmetric Hermitian is used. Note that V is orthogonal to W. So there is a, when we say V is orthogonal to W, there is a, there is an order. Okay? It is V and then W. Okay, so, but it is independent is what we want to make now. V is orthogonal to W if and only if W is orthogonal to V, since this is, in the real case, and bar in the complex case. Okay, and if one of them is equal to 0, the other one also has to be 0. Okay. So again, it is only when it is 0 that this argument will work. If it's a non-zero real number, of course, V dot W need not equal W dot V. Okay. But because these are real numbers, as in particular 0, this is okay. Okay, this is so this is just and if this was the usual dot product on a real vector space, this is exactly the definition of orthogonality. Okay, so just see, especially if the form is indefinite. So just one word of caution. Okay, consider the indefinite form. When I say form, I'm just describing the matrix. Okay. 1, 0s, 1, 1, minus 1. Okay, so this was the Lorentz form on R. Okay, and right, if we take the vector 1, so if V is the vector, or if V is a vector 1, 1, 1, and 3, okay, then V okay, should be 0, right? Please check. Somebody help me. Right? Sorry, I meant to. Sorry, this is 0. Okay, if it's not, please check after the lecture. If it is not, I will fix it. Okay. I just didn't check the numbers correctly. In an indefinite form, so that is non-zero vector is perpendicular, is orthogonal to itself. Okay. So this is okay. We will just live with it. Okay. We will take this as a definition without worrying about such weird consequences. But this is okay. We'll live with it.
Sir, I think the 3 should be a root 3.
Root 3. Okay, that is what I was. Okay, thank you. Yes, it should be square. Yes, thank you. We will live with it. Okay. just okay, so let us not worry about this issue that non-zero vectors could be orthogonal to itself. To them. Okay. I mean, a non-zero vector could be
Sir,
orthogonal.
is the indefinite form just a name?
No. Indefinite means neither. I mean, not positive definite, not negative definite. I mean, not.
Sorry, sir.
Indefinite means not semi-definite in either direction. Okay. Yeah. That's what it means. It's not the name for Lorentz form. It is
Yes, sir. I forgot it.
yeah. I mean, Lorentz form is the form of the name for that particular form I wrote. Okay. It has applications in relativity theory, which I do not know what the applications. Okay. So this is what time is it? Okay. So note that if W is a subspace of V, then we can restrict this thing to W. Okay. So in other words, just only consider V comma V, where V is inside W. So then this thing is symmetric. I mean, if it's in the real case on W, if and only if it is symmetric on V. Okay. In the real case. Okay. Similarly, Hermitian in the complex case. Because whether it checks symmetric, whether one check the condition that checks whether some form is symmetric, I mean, real symmetric or its complex Hermitian is universally quantified over all elements in V. Therefore, it is also holds for elements of W. Okay. So it is just for that reason. It is just the condition is preserved. Okay. So now the orthogonal complement definition. The orthogonal complement of I should say no, sorry, orthogonal space of W in V is this. Okay, so which we will denote by W perp. Okay. This symbol is called perp. In LaTeX, the symbol is called perp. So I will just refer to as W perp. Okay. W perp is V inside V such that V is perpendicular to W or orthogonal to W for all W inside W. Okay. So the sort of things like vectors, self-orthogonal, etc. So I mean, all of those things are allowed. Okay. Just formally take this as a definition and define orthogonal space like this. Okay. Definition. An orthogonal basis so I mean these are sort of related definitions, but all of them hinge on the notion of orthogonality in that vector space given by the given form, a symmetric or Hermitian form. Okay. Orthogonal basis of V is a basis V1 through Vn such that Vi Vj is 0 for all I different from J. So this is a basis in which the vectors are pairwise orthogonal. So we'll worry about orthogonal basis and what does the matrix look like, etc. In a little while. Definition. A null vector in V is a vector V in V such that V is perpendicular to W for all W inside V. Again, one shouldn't be completely I mean, definitions look like the way it is defined for dot product, but one should allow for these things because it is not clear what the form is. So, okay. So maybe sorry, maybe 1 minute. Let me just think about an example so that this definition is not confusing. Just give me 1 minute. Yeah. Okay. So here is. I was just okay. So suppose, for example, let be the symmetric form. So when I say symmetric form, I mean a real symmetric form on R2. The word symmetric is associated to real forms, real vector spaces and bilinear forms on them, while the word Hermitian is always associated to complex, given by the matrix 1, 0, 0, 0 in the standard basis with respect to the standard basis of R. Okay. So then let us look at, so then E2, which is 0, 1, is a null vector. Okay. So why is that? So if you take any vector here, so let V be in R2. So let us say that this is some AB. Okay. Then VE2 is just AB transpose of V times this matrix. Okay. And this is just 0, 0. Just check. Okay. Because forget about the left. The right hand side, this matrix times 0, 1 will just pick out the right column, which is 0, 0. And then irrespective of what A and B are, we will just get 0. Okay. So therefore, this is a null vector. Okay. Definition. The null space of the form is the set of all V such that V is perpendicular to W for all W inside V. Okay, and this note that this is actually by definition V perp. Notation. So there's a lot of definitions, a lot of notations. Please read it and try to write down some examples if something is not clear, or ask. Okay, so sorry, I have to give this barrage of definitions, otherwise. Definition. Form, when I say form, I mean the symmetric or Hermitian form is non-degenerate. Okay. If its null space is trivial. It's just 0. Okay. Of course, 0 is orthogonal to every vector, because 0 if you take the bracket product with 0 with any other vector, we will get just 0. Okay. So this is it is in the null space of the form, and if the null space doesn't contain anything else, we will just call that form non-degenerate. So remark, this form is non-degenerate if and only if for all non-zero v, there exists a v prime such that v prime is not zero. Well, of course, v prime also has to be non-zero, but that's not true. So this is non-degenerate. Okay. Okay. So one more definition and one lemma, and I will stop. But please read and think about these things. A form definition. Let be a form on V. Okay, symmetric or Hermitian as the cases on V. Okay. It is, we say that it is non-degenerate and W a subspace of. Let W be a subspace of. Okay. Say that this form is non-degenerate on W if its restriction to W is non-degenerate. Okay. So that is, for all W inside W, there exists W prime inside W, W not equal to 0, such that W prime is not 0. Okay, so let's go back to the. If you take W to be the, if you take W to be the span of E1, then this thing is non-degenerate on W. Okay. So I will give an example where on the larger space something is non-degenerate, but there is a subspace on which it is degenerate. It requires a little small computation. So I will do it. I will outline it in the exercises, and maybe just time for you to think about it also. So okay, but that's also possible. It is possible that on a larger space some form is non-degenerate, but on a subspace it is actually degenerate. That's also possible. Here we have seen the other way, that on a subspace it is non-degenerate, but on a larger space it is degenerate. Like in this example, on the span of E2, it is degenerate. Or also on V, it is degenerate. On R2, it is degenerate. But on the vice versa is also possible. So I will on R2 and on the span of E2, it is degenerate. Okay. Just one statement, and I'll stop after this. On V is non-degenerate on W, if and only if W intersect W perp is 0. So this is all the vectors in V that are orthogonal to, a vector in V that is orthogonal to every vector in W. Okay? So if that set doesn't contain, that doesn't intersect W, then it will be non-degenerate. Okay? So proof, anyway, it just follows from definitions. Therefore, I am just going to leave it as an exercise so that you are able to sort of internalize the definition. There's nothing much in the proof. It just follows from definitions. So it's a good idea to write it out so that you understand the definitions. So I'll stop here, and I will add some. I've uploaded some few problems, but I will add a few more that actually perhaps will help you understand the definitions and do some small computations with it. Okay, I'll stop here.